Hello all. Good afternoon. My name is Mahesh Subramaniam from HPE Networks, responsible for a data center platform software team. And with me, Vlad is there, who is the key engineer from Broadcom, working on heavily on nINC with a lot of open forum like UEC. And today we are going to discuss about nINC Manager for AI Fabric. And we are segregated into two parts. The part one, I'm going to talk about, go to the next slide. I'm going to talk about what network collective means, what is collective means first, and why it is so important to move the collective operation to network and fabric side rather than putting it into endpoint or GPU side. That is the fundamental question. That's the main reason for this session. And the second, I'm going to talk about what are the product availability here for nINC and how the open community like this can take those concepts and implement and to move forward. And part two, Vlad is going to present about what is nINC Manager means, what is the definition of nINC Manager, and how the nINC Manager can work on AI Fabric in Ethernet infrastructure, and some call for action from the SONiC side. That's what we are going to discuss. And I know though a lot of people here knows what collective means, but few people, for them, I will explain a little bit about the basic of collectives. In general, in AI infrastructure, if you want to train a model, usually if it's a small model, you can do it in 8 GPUs, which fit into one server. But if you're going into the large models, it will be maybe tens or hundreds of GPUs you need it. So you need multiple servers. When you have a multiple servers, that means you need a fabric. That means claw architecture, leaf and spine. So when you have multiple servers, and if you want to train a model, and you have to group those GPUs, when the training is completed or the iteration is completed, there will be a results. We'll call it as a gradients. That's our very fundamental things. So those gradients needs to communicate, needs to synchronize with all the GPUs, the 100 GPUs. How it's going to communicate? It's communicated via this concept called collective communication. That's what it is. And when you're talking about collective communication, there are a lot of methods are there, like all reduce, scatter, a lot of things are there. But the fundamental idea here is that everything is happening in general infrastructure right now, today. It's happening in the endpoint, in the GPU side. But the collective operations require communication, not a compute. What I mean here is that we need a more bandwidth for collective operations, not a flops, loading per operation not required. It may be required somewhat, but not much. So the bandwidth is important. So moving this collective operations from compute side, endpoint to network will be more beneficial. That's a fundamental idea here. Why? Because even when you move to the network side or fabric side, the switch, for example, 51.2 terabit switches, we have 64 into 800 gig ports are there. There are a lot of bandwidth. So moving the collective operation to the switch side will be more beneficial. One, you can see it here, the collective operation via fabric, we can predict the latency and it will reduce the tail latency. And also we are reducing the data copies, so increase the bandwidth utilization, so the job completion time will go down. That is the fundamental KPI, right? If you take any AI infrastructure, the job completion time needs to be low. So these are the methods. If you're moving it from the collective operation from endpoint to network, you have a lot of advantages. That's what I can say here. And go to the next slide. So how it happens, right? How you are moving the collective operation to the network side, and that's where the nINC Manager comes to the picture. Vlad going to explain in detailed way, but in higher level, what we are doing it in the classical fabric topology, usually the gradients from G1, G2, G3, G4, usually it will defined by the GP1 and GP2 or GP4, and this information, the RDMA packet, exactly the BTH header, base transport header, will go to the spine 1 as well as spine 2. With the nINC Manager, what will happen, this INC manager will create the tree topology. It will select the root. Right now, the root is spine 1. So the data copies will not go to the spine 2. Always it will go to the spine 1, and it will summarize that gradients, and it will propagate wherever the leaf, wherever the endpoint it want to communicate, it will communicate. That is the biggest advantage. How it does? The INC manager, the gRPC will communicate with the GPU, and the GNMI will communicate with the switch. So it will create the whole fundamental topology, tree topology, and it will identify the particular root spine, and the spine will communicate to all the leaf. That's how you're reducing the communication in the fabric infrastructure. Go back. Now, I think Surendra explained about in the last session about TH Ultra. It's not about product pitch, but the main point I want to communicate here is that in this open community, this INC manager, INC concepts are available as of today. So you can go ahead and take this opportunity to build and move forward with this INC manager concept in our AI infrastructure. That's one. And the second, how we are doing it, there are silicons are available. For example, TH Ultra is one of the silicon, the INC is supported. What we are doing as a vendor, go to the next slide. Thank you. So what we are doing it, in the TH Ultra, we are evaluating this product in our company, and we are doing a lot of proof of concept, not only for INC, for various use cases. So soon that INC manager in cooperation with our product and INC collective engines also get created. So we will show the demo also. Maybe next session we will show the demo, and I mean next day we'll show the demo. But what I'm trying to mean here is that take this advantage and take this one into the SONiC community and build your INC manager, INC collective thing. And Vlad is going to explain how to do that, and a lot of call for actions also there. You can take it forward. So Vlad, with that you can do that. Yeah.
All right. So I'm going to start off with the basic architecture that we're going to use for the AI fabric. So the main thing we're trying to do here is to offload all of those collective operations into the fabric. So on the GPUs, we've got plugins. So the GPUs can run either CCL, libfabric, or some MPI. We've got plugins. Next, at the start of the job, these GPUs will try to form a group. They talk to the INC manager. The INC manager allocates a tree for that group. And then that tree can be used for a number of collective operations. So the INC manager can operate standalone, or it can work with some load sharing facility to allocate resources for the INC tree. So the INC manager is at the heart of all of this. It is a daemon that facilitates collective offload. So it is aware of the network topology, and when a tree needs to be allocated, it is the arbiter of those resources needed for the tree. The INC manager is only involved in group management issues, such as group setup, group teardown, or the monitoring of the group status. But otherwise, it is not involved in the collective operations. The GPUs use a custom gRPC service to talk to the INC manager in order to do group setup, teardown, or whatever. And the INC manager uses GNMI to configure the switches to operate the INC tree. So in order to interact with the switches, we have developed an INC Yang model. Upon group creation, the IAM goes to each switch involved in the tree and sets up a Yang container. That container contains all of the relevant info for the group. So it tells the switch who its neighbors are, so which GPUs it's talking to, if applicable, what upstream switches it's talking to. It provides all of the IP addresses that need to be used, and also everything required to set up the QPs between the GPUs and the switch, or of course between the switch and the next hop switch. To monitor the group status, all the IAM needs to do is watch a Yang node that changes its status if the group happens to go down due to some error. And finally, when the group is no longer needed, the IM goes to every switch and deletes the grouping, thus tearing down the tree. So we plan to release the nINC manager as an open source product. Right now, the scope is that it's a standalone reference implementation, so no integration with any load sharing facility will be there when we release it. It can support any network topology, so you can do fat tree, you can do leaf spine, or you could wire up the network in an unexpected way, and things will still work. And for what it's worth, it is written in C++ for those looking to integrate it into their other products. Now, let's talk a bit about the performance that you get with Tomahawk Ultra. So as a baseline, we've used OpenMPI with Rocky, and we're doing all reduce. So the point-to-point communication is done using the ring algorithm. And of course, we compare that to how all reduce performs when we offload it to TH Ultra. So as you can see, we consistently get a 2x performance improvement all across the board. And the numbers are very predictable, so there's very little variation from run to run. This also scales well with the number of nodes. Here I'm showing 16 nodes, but we've run tests all the way up to 64 nodes. So, as a call to action, first up, we would like there to be open programmable interfaces to configure and monitor whatever collective offload is happening in your network. This goes for both scale-up and scale-out fabrics. The second thing we're working on is supporting nINC in SAI. We've got Jay Kumar from Broadcom already working on this. And we would also like to incorporate GNMI support into SONiC. So that basically means that we would like to standardize the Yang model. And of course, then take it to SONiC and write the rest of the software to interact with the model. And that's about it. So I'll be happy to take any questions. In fact, we'll be happy to take any questions.
So quick question, in a nutshell, the nINC manager tells GPU who the root is?
No, it does not tell the GPU who the root is. It tells the GPU who the next hop switch is.
So you essentially want to, is it similar to multicast where instead of creating multiple copies of the GPU, I send one and it fans out, or?
Are you talking about broadcast or?
When I have to reach, I'm trying to understand how it makes GPU not do more.
All right. So say you want to do an all reduce. Configures the GPU with the IP address of the Tor switch, and then the GPU starts blasting its input data. Every GPU does that. After the data gets aggregated, the next hop switch will eventually send the output data over to the GPU, and in fact to all other GPUs if we're doing all reduce. Does that answer your question?
I think yeah.
Okay. And also I will add one point here. You're kind of correct, because it's in multicast there is a concept called assisted replicator. Basically what it will do, spine 1 can be assisted replicator, it will propagate the information. It's nothing related to with the gradients and all reduce, but the concept what you're understanding, that's almost correct here. Yeah.
Thanks.
Yeah.
No problem.
Hi, there are two questions for me. One is how big can a gradient get? And
how big?
Like in terms of data?
So we've got a limit of, I think, 4 gigabytes. Of course, if your collective is larger than that, you can split it into 4 GB collectives and then do them serially.
Okay. And is there a limit on how many jobs that can be run parallel?
No. So the limit simply comes from not having enough resources in the network. So if all of the links are used up, then you cannot spin up more groups or more jobs.
And the spine will be aware of for what job am I doing the gradient sum for?
So the spine doesn't care what job it's performing, it's doing the computations for, nor does it care what the computations actually mean. It just sums up numbers, or maybe does min or max. You get it.
Hi, thank you for sharing this ink manager.
Hello.
So what you said seems to be a little bit different than the previous talk by OCI and Broadcom. In that presentation, they did say they have roots as the all reduce for the all reduce case.
Sorry, I didn't get that. So
in the previous presentation from OCI and Broadcom, for the all reduce diagram they used, they did have a root for the all reduce.
I didn't get that. They did have a what?
So he's saying the last presentation from Surendra, he didn't see the root because the concept there is to introduce INC, what is INC means. But you can call it as a root, or you can call it as the main spine, right?
Yeah, so
the concept is same.
Okay, so I think I get your question. So if you've only got one switch, or if all of the GPUs trying to perform the collective operations are in the same rack, they will only talk to one switch, to the TOR. Now, if they happen to be in separate racks, the two TORs will aggregate the results for you. They will compute the partial results for you. But you need a third switch to aggregate the results from the two TORs. Now, that will be the root of the INC tree.
Yeah, that's the root, right? I mean,
yes.
You have a root here. So yeah, my question is that, so when this root fail for some reasons, does the NIC or the GPUs wait for the ink manager to update the new root, or it will react by itself?
No. So if the root goes down, or if any of the switches goes down, then the entire group goes down.
Okay.
Yeah. Nice work, by the way.
Thank you.
So kind of two questions. One simple one, is the GRCP, is it running on the CPU or is it running on the GPUs?
Yeah, so it's running on the CPU.
Oh, okay,
It uses regular TCP to talk to the...
Yeah, okay. I thought so. I just wanted to clarify.
Yeah.
And second, I meant to your call to actions. I mean, I know that like both the Ultra Ethernet community and the UA-Link community are both working on INC and have open interfaces already defined for INC infrastructure. How do you guys, I mean, do you guys work with them, or how do you guys think of
No,
that
he's working heavily on
yeah.
open forum like Ultra Ethernet Consortium,
Okay.
by the way.
Yes,
And yeah, you can talk about it.
I am not involved in UA-Link.
Yeah.
I myself personally, I am involved in UEC.
UEC,
Okay.
yeah.
And I do a lot of work there to bring this kind of INC to UEC.
Okay, so you are working with them, and that's potentially part of the
Yes.
discussion. Okay.
So if this work goes forward, there will be kind of like the same thing at UEC, except that it will use the Ultra Ethernet transport.
Yeah, okay, got it, thank you.
Hi, looks like we have a single route for where all the computations are done. Instead, why wouldn't we just flood the packets over and the leaf node closest to the GPU does the summation?
No, so every switch does summation. So if you've got a multiple tier top tree, then the switch at the top will only get the results from the switches, the partial results from the switches it's directly connected to, and the intermediate switches will get the results from the, let's say, from the GPUs.
My suggestion was, why does it need to follow a path up to the root? You could just flood to the destination leaf, and the destination leaf sums everything up before it gives it to the GPU.
Well, that uses up a lot more bandwidth. So if there's only one switch doing the summation, it has to take in the same amount of traffic from every GPU. So if you've got 1,000 GPUs, you're going to have all of them blasting data to one switch, and that doesn't scale.
But isn't the root technically getting all the traffic anyway, and is it not the same constraint?
No, it's not getting all the traffic. So the intermediate switches compute intermediate results. So if 3 GPUs each provide 1 gigabyte of input data, the switch, the TOR, will only output 1 gigabyte of data up the tree, not 3.
Okay. And how much is the INC bandwidth, the percentage of the total bandwidth in this network?
Are you asking how much?
I mean, it's only a concern if the INC bandwidth is a large percentage of what is in the AI fabric. Is it a small percentage of the AI fabric, and then does it matter?
So we don't know. It depends on the workload. Right now, we've got the Tomahawk Ultra in the lab. As far as I know, there's been no large deployment of Tomahawk Ultra yet.
Thanks.
The hopes of you can answer this. In Tomahawk Ultra, where on the data path the compute part of this partial or reduce happen? Does it happen on the embedded processor, or is there dedicated engine on the data path for it?
No, we have a dedicated engine for that.
We have a INC engine in Tomahawk Ultra that will take care about it. Yeah.
All right.
Okay, awesome. Thank you.
Thank you.